Good morning, good afternoon. My name is Thomas Mueller, and I'm the Director of Applications for the AFM business at Bruker. I'd like to welcome you to this installment of the Bruker AFM webinar series. This presentation today is titled, How Does Atomic Force Microscopy Work and What Can It Do? It's presented by Dr. Chunzeng Li. Before I introduce Chunzeng, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar, and if you have a question, please type it into the questions dialog box on your screen. We will accumulate these questions through the presentation, group them together, and answer them at the end of the prepared remarks. Quite often we have more questions than we can answer in the session, and in those cases we will be sure to follow up with answers via email afterwards. Also, if you'd like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within 1 week in the webinar section of the Bruker AFM webpage. As a follow-up to this presentation, you'll also be receiving an email with this link. Finally, when you exit the webinar software, you will be asked to take a brief survey. We'd very much appreciate if you take the time to complete this, as it helps us pick the topics that are most important to you and to generally make this series better. So let's get started, and let me introduce our presenter, Dr. Chunzeng Li, electrochemistry and electrical applications scientist. He's in his 14th year with the company. He received his PhD in physical chemistry from Xiamen University, China, and he's the author of 26 international publications and 2 patents. So with that, let me now turn it over to Chunzeng for his talk titled, How Does Atomic Force Microscopy Work and What Can It Do?
Thanks, Thomas, for the introduction. And thank you, everyone, for joining this webinar. Again, I'm Chunzeng Li, Senior Staff Applications Scientist with Bruker. Today, I will talk about how does atomic force microscopy work and what it can do. I have some. Hello, we just had a technical glitch, and now we come back again. Can you hear? So today we'll talk about how does atomic force microscopy work and what can it do for you. atomic force microscopy is one of the members of scanning probe microscopy family. And 30 years ago, scanning tunneling microscopy was invented by Binnick and Raman at IBM Zurich. And 5 years later, they got a Nobel Prize. And why did they deserve that? Because for the first time, they can see atoms, real space atomic resolution images of surfaces. In 1986, atomic force microscopy was invented. Now let me point out the major changes or the revolution of AFM technique. In 1986, contact mode AFM was invented, and then 1993, tapping mode was introduced by then Digital Instruments, now Bruker. And in 2009, which is just a few years back, we have PeakForce tapping mode invented again at Waco Bruker. So how does atomic force microscopy work? So the concept is fairly simple. You slide a probe across the surface to get the topography. It's simple like this. Now, think about if you close your eyes and you still want to know how your friend's face looks like, what do you do? What you can do is you can close your eyes and run your finger across his face. And make sure your finger will follow the up and down on his face. Let's say if your finger comes to the nose, your finger will lift, so it will follow the up and down. And if you record the position of your fingertip, and then you will map out the contour of the face. Of course, you scan point by point, and line by line, you do a raster scan, and you record the position of the fingertip. You get the topography of the surface. And this is how simple the concept is. Of course, there are some tricks, because for atomic force microscopy or scanning tunneling microscopy, you get very, very high resolution. That's the only difference. And we are talking about atomic resolution, molecular resolution, nanometer resolution. So the trick here is, of course, your tip has to be sharp. It's a sharp needle, as you can see. And I can go back one slide. And here you can see AFM probes, and there's a cantilever, and then there's a tiny, tiny tip there. And the very end, we are talking about a few atoms, few nanometers. And similarly, for STM probe, it's a really sharp metallic needle there. And in the very end, you can imagine it's only one atom that protruding, sticking out. So you have a sharp tip. And next thing, the next trick is how to follow the up and downs of the surface precisely. And this is where the scanning component comes in. So down here under the probe, and there's a scanner. This is a tube scanner, and it does 3D motion. First, you need to scan the probe or the surface, the sample against each other in X and Y. So you get 2D scan. In the meantime, in order for the tip to follow the up and downs on the surface, the tip must adjust its Z position. And that's why in this scanner, and you can move in this direction. So you get a 3D structure of the surface. So the other thing which is not shown on this image is, or the trick for the tip to again precisely follow the sample is how to adjust the tip Z position, right? So you have to have a parameter or physical quantity that depends on the separation or distance between your tip and sample. So when you scan point by point, at each location, the tip stays right on the surface or a certain distance, a constant distance above the surface. That way, you can trace out the surface topography faithfully. Now, in STM, in scanning tunneling microscopy, that physical parameter or entity is tunneling current, because tunneling current depends very sharply on the tip sample separation, the gap there. It decays exponentially. Now, for atomic force microscope, though, the force, as you know, depends on the tip sample distance. So the force is really the distance sensor, and if again you have a way to maintain a constant force between the tip and sample while you are scanning from point to point, and then you can trace out the topography. The next thing is how well you control the force. So how do you know the force is changing? And that's where the cantilever in this probe, the micro cantilever, is used for. So under force, this cantilever will deflect, will either bend down under attractive force or bending up if it's a repulsive force. And that bending can be very, very tiny. To detect that, one common scheme is to use beam deflection detection. That is, you shine a laser on the cantilever, and then it's reflected back to a photodetector. So when the spot moves, and it knows how much it moves. That's how the force is detected. Now let's take a look how the first AFM works. That's contact mode. In contact mode, the tip is always in contact with the sample. So when you scan the tip across the surface, and the most common way is to keep the force constant when you do that. Of course, if you look at here, you have this scanner there. You have the controller that's to maintain a feedback loop will keep the force constant. So there is contact mode works pretty well for hard samples. However, for some fragile samples, when you slide the tip across, you may damage the sample. So in order to apply smaller force, tapping mode AFM was introduced in 1993. So the way tapping mode works is the tip doesn't contact the surface all the time. Instead, it contacts the surface intermittently. The way it works is you have this cantilever, and then you oscillate, you vibrate the cantilever at its resonance frequency. So when it's far away, let's say, and the oscillation amplitude, which we call free air amplitude, that's big. And then when the tip approaches the surface, when the tip feels the force from the surface, the amplitude will drop. So this oscillation amplitude depends on how far the tip is from the surface. So you can use this tapping amplitude as a sensor to regulate tip sample distance. Since the tip is not in constant contact with the surface, so that's why it's light. So the force is much smaller than in contact mode, and also it eliminates the lateral force, which can tear the sample. However, in tapping mode, the force is not directly controlled because the amplitude changes or respond to the force not in an instantaneous motion or manner. A few years back, Bruker introduced PeakForce tapping mode. And you can think PeakForce tapping mode is a hybrid or contact mode and tapping mode. So again, we are oscillating the probe, but not at its resonance frequency, at the resonance frequency of the cantilever, but at a much lower frequency. And this way, we can control the oscillation, precisely. So the way it works is, let's say you oscillate the Z position of the tip, and then at the same time, you monitor the deflection, which is the force the tip experiences. So for example, when the tip is far above the surface, let's say in point A, you don't feel any force. And when the tip approaches the surface, and when it's close enough, it feels attractive force. And when you go further close to the surface, the tip will snap into the surface. And if you go further, then you can see it experiences repulsive forces, and it's getting bigger and bigger. So what we control is the maximum force, and which we call the peak force. So we control that one, the peak force. So when it reaches the maximum force we want it to go, then it turns around to retract from the surface, for the tip to retract from the surface. And then you can see the force, the repulsive force is decreasing. When it's far away, far enough, the tip will break off the adhesion force from the surface and it will snap off the surface. You can see it goes back to the baseline until point E, there's no force. So that's how the force is changing in one peak force tapping cycle. Usually, the oscillation frequency is a few kilohertz. And from this force curve, we can see you can reconstruct the force distance curve as shown in the right. Again, by controlling the peak force and feedback on it, you can get topography of the surface. So the major difference for peak force tapping mode is you can control the force directly and instantaneously. So you can have a very small force between your tip and sample. Here is one example to show how gentle it can or how small the force you can control. And we can control the force to below 100 pico-nanonewton, 100 piconewton. In this example, it's a fairly challenging sample. It's a protein membrane on the surface, and usually it's fairly hard to do. But here with PeakForce tapping mode, we can emit this soft sample fairly routinely, easily, and with high resolution. On the right, in the high resolution, which is 100 nanometer scan, you can see individual protein molecules there, and you can also see, let's say, I'm pointing to a protein molecule there, and you can see in the center there's a hole. That's the opening channel of the protein. So that's where the ions comes in and out of the cell. So you can see that. The other benefit or advantage of PeakForce tapping mode is at each point a complete force distance curve is obtained. And from this force distance curve, you can learn quite much about the sample. For example, you can see how much the tip is deforming the sample, how much deformation the tip causes the sample. And that tells you, or that's a matter of how hard the sample is. And from the retracting branch, the blue part, and you can, from the slope, you can tell or how elastic of the sample, the elasticity of the sample. And there actually you can get the modulus quantitatively. You get a number for that. And from the, again, on the retracting branch, if you measure the force difference between the very bottom and to the baseline, you know how sticky the sample is. That is the adhesion. And from the area enclosed by the approaching curve and the retracting curve, you get the dissipation, how much energy was dissipated during one PeakForce tapping cycle. So you get mechanical properties of the sample. Pretty much like this. Let's say when you use your finger to touch, let's say, to touch my hand or face, and in some area you feel it's soft, in somewhere if it's, there's a bone there, you can feel it's hard. In the same manner, you use AFM tip, you can get the mechanical properties of the sample in numbers. So I want to show you one example, and this is a polymer blend, for cable polymer blend, and it has different components there, different polymer components there. Now, if you want to know how those different polymer components blend together, mix together, and where they are, and you can use the elasticity map, the modulus map. And from this map, you can see three different colors, and the light blue or white, almost white, and the blue, and also the dark area. Now, if you do a analysis, bearing analysis, you can see the distribution of the modulus. Get 3 peaks, A, B, and C peaks that corresponding to different polymers. Now, if you compare the modulus to the bulk modulus of different polymers, you know which is which, and you know where they are, how well they are mixed, and how much they show on the surface. You know the distribution. So PeakForce tapping mode gives you a way to differentiate materials by its mechanical properties. So I want to now show you, or you may have this question, so where AFM will work, or in what kind of environment it will work. Initially, both STM and AFM was done in vacuum. Now, not until when we make AFM and STM work in air and in liquid, and then its use was more widespread, it's more popular. So anyone can use it in different environment. Here, you can immediately recognize this is a blood cell. And to image biological samples, you want to measure that in vivo. That is, in its physical condition or environment. So this is done in liquid. At the left, it's a healthy red blood cell. And on the right is an infected one. You can see the infected blood cell has a very different shape, and also it has some little bump or knob-like features on it. But the point here is AFM works in liquid, in air and in liquid. Another example for biological samples is a smaller one. It's DNA. So not only you can see the DNA chains, and you actually can see the double helix structure there. You can see the little features there. And the spacing is about 3 nanometers. Again, this is done in liquid. Let me show you a little video here. So those images are taken sequentially, and you can see some part of the DNA chain is immobilized and some parts are moving around a little bit. That's because the chain is, some part is anchored to the surface by ionic force. Here is nickel ions, and some part is not anchored, so it's moving around. But again, this is to show you AFM works in liquid, and it gives you high resolution. Another application of AFM in liquid environment is electrochemistry. So here I want to, if you wonder how does AFM works in liquid, and here this picture will illustrate that. Again, here you see, what you see is icon scanner, and you see the laser spot there. So, and here there's a tip holder, and there's a tip there, and you can dip this tip into a cell, electrochemical cell, which is filled with liquid, of course, and to reach the surface and image it. I just want to show you one example of that. That is, when you charge a lithium battery, probably you are very familiar with lithium battery. In your laptop, in your cell phone, there's a battery that powers up the devices. Now that battery is a lithium battery for its high energy there. Now, if you wonder when you charge or discharge the surface, what's happening, and what you can do is to use AFM, you approach the surface, and while the charging, discharging, which is going on, you see what's happening on the surface. In the left, when we ramp the potential from 1.5 volts to 0.36, you can see it changes quite a bit. That's because when you charge the battery, lithium ion will become lithium and intercalate, insert into the silicon anode, so it's getting bigger. And also some other reactions going on, so it's getting bigger. It's changing there. So you can monitor electrochemical processes in situ real time. now we get a feel that AFM or scanning probe microscopy, its primary role is to image the surface, to see the surface. There's a notion saying if you can see it, then you can manipulate. This, I think, is the very first image demonstrating actually you can move atoms. So this is done with a low temperature and ultra high vacuum STM. And in the first image, those white dots are xenon atoms on nickel surface, on the nickel surface. And use a STM tip, you can move xenon atoms around, and you can put them into different into places and to spell out. This is done by Eigler at IBM, and he spelled out IBM, and it's quite amazing. That's 1990. So you can manipulate. And if you do the same thing with AFM, of course, you can do it in ambient conditions. And here, what we did is, you can use AFM probe to push the nanotube, carbon nanotube around. See, you see this carbon nanotube, and you push it in, you get a kink there. You put it here, you get a kink, you get a curve. And if then you measure the electronic properties, conductivity, for example, it will be different. So you can, again, use AFM, STM to manipulate on atomic scale, nanometer scale. So again, for the IBM letters, that make people imagine, make people think, maybe we can build things up from atom level. So give you a bottom-up approach for building tiny structures. Now what I have talked is the major mode, right? Or we call primary mode. And AFM actually opens the door for you to know more, not only the topography, not only that. Just imagine if you have a probe, for example, it's also conductive, and then while you are imaging, you can also have current flowing through this probe. You apply a bias between your sample and tip, and then current will flow. You have a current amplifier. Then you can measure what? You can measure conductivity for the sample. And here's one example. On the left, you can see carbon single wall carbon nanotubes were laid down on a silicon substrate, silicon oxide substrate. And you get the topography at the left by AFM. And on the right, and if you measure the conductivity, you can only see that along the carbon nanotubes, you see current because it's conductive. And on the rest of those particles, they are insulators, you don't see current. So you can get a current map or conductivity of the sample, again, on a nanometer scale. You can point to a different location of the sample or different structures on the sample. You can measure the IV curve. You get the IV characteristics of different structures or features there, or materials there. Similarly, you can measure resistance. And here, we use a logarithm amplifier, so you can measure without changing gains. You can measure very, very small current. We are talking about picoampere current all the way to milliampere current. And what special about this mode is it covers a wide range. You can measure very small resistance to very big resistance. And it's particularly useful if you have a semiconductor sample. For example, for semiconductor, this here is the silicon, and when it's doped, lightly doped, here it's 10 to minus 14, and all the way to it's highly doped, 10 to 20. And you can see the resistance. So let me see. The blue one shows the carrier constitution, and the red one shows the resistance. So you can see the resistance has a linear relationship with the doping density, and from here you can see different doping profiles of the sample, and that will be useful for electronic devices. And here it shows you what kind of resolution you can get. Actually, can be better than this. And here it shows you a PMOS NMOS transistor. And you can see where the channel gate is and where the source and drain is. So it's a quite a useful, powerful technique for semiconductor applications. And as you know, now the device structure is getting smaller and smaller, and SSRM, in this case, spreading resistance microscope, is one of the tools. In some cases, it's the only tool for you to see the doping profile, doping structure of those devices. The other technique is scanning capacitance microscopy. And here, again, you have a conductive probe, and then you have a silicon sample substrate there. On top of there is silicon oxide. Now you can see the tip, and your sample forms a metal insulator semiconductor capacitor. It's a capacitor there. So, and there is a tiny capacitance between your tip and sample. And scanning capacitance is going to measure that capacitance there. And that capacitance, again, relates to the doping concentration of the sample, of the semiconductor. Here is one example to show what it can do. And at left is the topography. And on the right is the SCM image. And clearly you can see not only the doping concentration in different regions, the N region, the P region, and the depletion region in between. It tells you whether it's N-type or P-type semiconductor, or N or P dope. Another electrical technique is you can measure the work function of your samples. Give you one example. So this sample is tin lead alloy. It's a solder material. So when you map them and you want to know where is your tin, where's your lead, and you can do this KPFM, or surface potential. And with this cavern probe force microscopy, you can measure the potential difference or work function difference between your tip and sample. So in this case, the darker area corresponding to the lower work function, that's lead. And the brighter area, the higher work function part is tin. So you can see how they mix together, and what's the potential difference there. Now imagine if you have different materials in your sample, and by comparing or looking at their work functions, you can figure out which material it is. Shown here is a combination of PeakForce technique mode, which is the advanced AFM mode, and with a frequency modulation Kelvin probe technique, which gives you high resolution. Now I have shown you very briefly, but I hope I give you a flavor, how AFM works and what kind of application you can use that. Now I want to touch on some of the trends. Now if you think back about how AFM evolves, you can see for AFM technique itself, it goes from contact mode and then technique mode and then PeakForce technique mode. And really it centers around this. How do you control the force better? How can you control precisely a small force? And the other thread is how to make this machine easier to use. And that one I didn't talk much, but we have, for PeakForce technique mode, we have scan assist error that that built-in algorithm to optimize the force, how much force to apply, and how fast you scan, and the feedback speed, so that you can, without the user too much intervention from the user, you can get very good image, decent image. So that's an easy use of the machine, and we are trying to get more and more information simultaneously. It goes way beyond just topography imaging. You get, as we said, with PeakForce technique mode, you get mechanical properties. And when we combine PeakForce technique mode with, let me show you some example, with conductivity measurement, which we call PeakForce TUNA, and you get all those information here, like the topography, of course, you get the modulus, mechanical property of the sample, adhesion, which reflects the chemical properties of the sample, and you get a conductivity map. So you get all those different information at one shot simultaneously. So you want to get more information, and also you wanted the information to be more quantitative. And the other one is we want the scanning to be faster and faster, so we can capture some dynamic processes, or to increase throughput or higher conductivity. Here I'm showing you a polymer, and that's melting. So you can see. So you can see the two front of this polymer when it melts, how it crystallizes and how the front, gross front moves. And it hits a defect. It goes around here. So for the scan rate here is 100 Hertz. So for one frame, it takes a little over 2 seconds. Of course, we want it to be faster and faster. So that's one trend, to scan faster. And here again, the polymer, but it's done at different temperatures. You can see the growth rate, how fast the front moves. At high temperature, it's much faster. Another part is to get a higher resolution. So with scanning with STM, the resolution is intrinsically high, but with AFM, of course, if you do it in UHV, it's not too bad. You can get atomic resolution, molecular resolution, and so how to do it more routinely in ambient condition or in fluid, that's still a challenge. But here we want to show you with a PeakForce technique mode image on calcite in liquid. So when the crystal dissolves, and you can see the atomic structure on different plates on the lattice. And also here is the model to show you where the oxygen atoms are. And yeah, so I want to point out for AFM, you can actually routinely get the lattice structure of the sample. However, if you want to see single defect, that shows the true atomic resolution. That's a hard part. Now, with PeakForce type mode and with the better constructed AFM, we can see atomic resolution. Here, another example to show polydiacetylene, and you can see the molecular structure there. In addition to the topography, again, with PeakForce type mode, you can see the mechanical properties, the stiffness, and the adhesion there. Again, with a high resolution. Another trend is people want to know not only how it looks like, the topography of the surface, and they want to know what it is. And one way to do that is to combine or couple AFM with some spectroscopy techniques. For example, Raman spectroscopy or infrared spectroscopy. As you're aware, for those optical or optical spectroscopic techniques, there's a diffraction limit. Now, with the AFM tip as an antenna there, it can detect the signal from the near field. And that one, so the tip, the radius of the tip really determines the resolution, and that can give you 10 nanometer spatial resolution there. And of course, at each point, you may get a full spectrum of this. And those peaks, the vibrational frequency of the molecules is a signature or fingerprint of the molecule, so you'll know which chemicals are right underneath the tip. Now here I'll show you one image on graphene, and on this graphene sample, it has several layers, as you can see on the topography. It has, one that's a single layer, and 2 layers, 3 layers, 4 layers there, and the step height there is 3 angstroms. Now with the Raman spectroscopy on the G band, you can see clearly some stair structures corresponding to the topography there. On the Raman D band, you see some high resolution defects there. And also you can see with the IR map at this wavelength, and you can see the difference. The layers. And here with KPFM, you can see the work function there. So you can really gather all the different information together and correlate with each other. So now here I want to summarize briefly. So I hope I have given you a flavor about AFM technique itself, how it evolves, and centering around better and better force control, from contact mode to tapping mode, and to the recent PeakForce tapping mode. AFM has really opened the door to this nanoscale world. It goes way beyond topographical imaging. You can access a wide range of properties like mechanical, electrical, magnetic, and chemical properties. And as you have seen, it has very diverse use, and this is really benefited from that it works not only in high vacuum, it works in ambient, in air, and it works in liquid. And it has been used by academic users and also industrial users for a real and for the trend is we want to make this AFM easier to use so everyone can use it without spending too much time learning it, and make it to scan faster so we can capture dynamic processes and make the resolution higher as you do care about the tiny structures there. And the other thing is more information are wanted quantitatively. And one big part is what it is underneath the tip. That's chemical identification. And with this, I thank you for listening, and we'll open up for questions.
Okay, yeah, thank you also from me, and thank you, Chunzeng. This is Thomas again. So let me quickly have a look at your questions, and I've already followed along as you sent them in. Just quickly collect a few here, and we'll start addressing them. We have maybe 5 minutes left to do that. So just a second. Yeah, one question coming in from you about AFM tips, AFM probes. Can you use the same tips for tapping mode and for PeakForce tapping mode?
I would say yes. But usually, depending on you can use the same tip for both tapping and PeakForce tapping. The choice or the options for PeakForce tapping mode is much wider. The reason is when you do tapping mode and you want the cantilever to be relatively stiffer. So when you move the tip up and down, you don't want the tip to get stuck into the liquid layer that's usually on the surface in ambient conditions. So the spring constant of tapping mode probe is usually stiffer. Now for PeakForce tapping mode, and if you want to control very small force, and you can go with a tip with very small spring constant, so you can achieve very light force or accurate force control. For example, you can use spring constant down to 0.1 Newton per meter, versus for tapping mode, it's a few Newton per meter or tens of Newton per meter. But on the other hand, if you want to use PeakForce tapping mode for mechanical property measurement, and for some samples, if it's fairly hard or the modulus is high, you want to use a higher spring constant cantilever, that could be a tapping cantilever.
Thank you. Then a number of questions in regarding some of the images. Image in blood cells, what type of probes were used there? Do you know which probe it might have been there for the blood cell image, or what would you use on such a sample?
I don't know exactly in that particular case. We have that's done by it's done by PeakForce tapping mode, and most likely it's done with what we call scan-assisted air fluid sharp probe, and that one has a spring constant of around 0.4 Newton per meter. So so you can use a small force. You don't deform the blood cell too much, right? So you want to apply small force there.
Okay, and maybe related questions there. So PeakForce tapping then can be used in fluid was a question, and how do you tune?
That's a very good question. For PeakForce tapping mode, you can use it in fluid and in air everywhere. Actually, it's much easier for it to work in air if you compare that with tapping mode. Now, in tapping mode, you do have to tune and to find the resonance frequency of the cantilever. And often in fluid, that's a problem because there's hydrodynamic going on there. When you vibrate the cantilever, and the fluid will move along, so gives you multiple peaks. So that's a challenge for tapping mode. You have to really choose, figure out which peak to use. Now for PeakForce tapping mode, it's not a matter at all. You don't have to tune. Let's say you can choose to oscillate the tip at a 2 kHz or 1 kHz or 0.5 kHz, whatever. So it's not related to the resonance frequency or the cantilever. You just use any. So there's no tuning process involved there. So it's much easier than tapping mode.
And thank you. And related to the liquid samples, the question of what environment the AFM was operated in, the red blood cell. Do you know, was that done on the perfusion stage on the catalyst? You also showed the lithium battery. Was that done in liquid? Was that in the EC cell?
So for the blood cell, actually, I don't know the detail there. It's done with PeakForce tapping mode. There's for that there's a liquid cell. I need to find out exactly which cell is used. I think it's a bio cell.
And the lithium battery, that was also done in liquid?
Yeah, so the lithium battery sample is done in electrochemical cell that's designed for dimension icon AFM. Yes, actually for that cell, not only it's in liquid and it's organic solvent there. And if you know about lithium battery, which I believe most of you know, that lithium is quite reactive in air, right? It will react violently with water or oxygen, so it cannot be done just in ambient conditions. It has to be done in an inert atmosphere. So what we have is we have the dimension icon AFM put in a glove box, and the glove box is filled with argon. So it's done in an argon-filled glove box. It's done in a cell that's sealed. When the tip is in the liquid and the cell is actually sealed, so the liquid won't evaporate.
Let me see. Let me move on. Oh, yeah. One question about PeakForce tapping. It says, did I misunderstand, or can you achieve atomic resolution in ambient conditions with PeakForce tapping?
You could, but it's harder to do in air than in liquid. Because in air you tend to have a water layer there. You tend to have contaminants. I would say one big part is really, can you keep the sample so clean? That's a challenge. Related as when you do STM and in liquid you see a lot of beautiful atomic resolution structures. Because in liquid, let's say you have a single crystal gold or platinum, whatever crystal there, and if you cover that with very pure water, and it can be as clean as under UHV conditions. So that's why it's easier to do high resolution in fluid versus in air. But still, you can do it.
Let me see. Let me make sure I'm catching up with the questions here. A question on Bioscope Catalyst. Can it be upgraded to have PeakForce tapping? Yeah, short answer is yes. In fact, nowadays it ships with PeakForce tapping standard on it. PeakForce tapping and Scan Assist. It can be upgraded also to have the PeakForce QNM package with the QNM channels. More questions? Oh, any comment on probes used for the DNA images?
Well, in general, you want very sharp tips. You want sharp tips, right? Because the weight is only 1 to 2 nanometers, so you want sharp tips, and you want small force, so small spring constant. For that, you can use Scan Assist Air Fluid Sharp, and also there are other probe options. I believe that's there is the other one is, I think it's released is Scan Assist No, it's FastScan DX. So yeah, there are different options there as well.
A question regarding some of the electrical data you showed. It says scanning topography. I assume this may be scanning capacitance. Can it be used to measure the doping level and the type of semiconductor, that mode? Can you apply that to small features? Could you apply that to nanowires? And the diameter is mentioned, 30 to 50 nanometer type diameter features. Could you use scanning capacitance there or scanning spreading resistance?
So for those, I would say yes. For now, for scanning capacitance microscope, the resolution is on the order of, let's say, 20 nanometers. I know there are efforts going on to make the resolution higher. And for those small structures, the more suitable tool will be scanning spreading resistance microscope. And the resolution can go down to 1 nanometer, few nanometers, so which is in line with the current semiconductor devices resolution. So I want to point out, though, so when you do that in air, since usually there will be a water layer on the sample, and then because the resolution is determined by the contact area. Now, if you have water, although the tip sample contact area, let's say, is 1 nanometer, because the water layer actually is conductive, that makes the effective electrical radius bigger, so you can only reach, for example, 20 nanometer resolution. But if you move that to for example, in a glove box, right, and if the sample goes through a vacuum to remove the water layer, and then in vacuum you can get to 1 nanometer resolution. Of course, you need a sharp tip as well. But yes. So
another question on electrical measurements is, can we also measure the polarity of a material if we using a conductive tip? Are there AFM modes for such thing? I assume polarity, electrical polarization, or electrical charges, or I'm not sure if this would refer to the polarity of the dopants, although I think we addressed that part with scanning capacitance.
Right, right.
Want to comment on?
I would say yes. So again, for dopant, yes, you know that, and also with Kelvin probe force microscopy, you can know the if you have, let's say, static charge on the surface, and you will know it's a positive charge or negative charge. Now, another one for polarity is probably, I don't know whether you are referring to piezo response force microscopy. Let's say you have different piezoelectric domains on the surface, and you have the tip on the surface. Now, if you apply a alternative, voltage to it, it's like a piezo, right? So, and that domain may respond to the electric field to expand or contract, and you can tell the polarity there as well.
Okay, good. Thank you. We're out of time now. We do have more questions. We'll follow up with email. Again, thank you for everybody for joining us for this webinar today. We'd appreciate it if you do answer our exit survey. It is also always very helpful for us to make future webinars better. And you'll also receive a link for downloading this webinar later. And thank you again, and bye-bye. Hope to see you, hear you again soon. Thank you.
Thank you.